Ciyuan Zhang, who's with the Department of ECE, present on estimation and distributed eradication of SIR epidemics over networks.
All right, thank you, Tom. I'm going to share my screen. All right, good afternoon, everyone. Thank you for having me. My name is Ciyuan Zhang, and my advisor is Professor Philip Paré. Today, our research topic is the estimation and distributed eradication of SIR epidemic over networks. So this is the WHO COVID-19 dashboard of the world. Since the outbreak, there have been more than 150 million COVID cases and over 3 million deaths caused by this virus. The pandemic has also caused excessive amount of economical loss worldwide. Therefore, one of the most pressing problems is to monitor this infectious disease through the testing data and mitigate the transmission of the virus. One of the biggest challenges for monitoring the infectious disease is the long asymptomatic period of COVID-19, and the patient could be infectious during the period. There is a time duration between the infection and the positive test result. So in this figure here, as we can see, patient 1 and 2 attended the same business meeting with the index patient. Patient 3 and 4 came to contact with patient 1 for a different amount of time. And it took different number of days for the 4 patients to obtain a positive test result since they became infected. Therefore, the testing data does not reflect the real-time infection over the population. It is rather a randomly delayed representation of this infection. Our target is to monitor the infection state over the population by capturing this randomness of the testing delay and to design mitigation schemes accordingly. In this research project, we consider a virus spreading over a network where the nodes are modeled after the 5 major metropolitan areas in northern Indiana. 2 nodes are neighbors if there is a major highway that connects them. We then introduce our discrete time SIR epidemic network model. In our model, each node in the network can only be represented by 3 states: the S, susceptible, the I, infected, or the recovered, R. And the dynamics of the 3 states are given in these equations. Here, the SI is the susceptible level at node I, and XI represents the infection level at node I, and RI represents the recovered proportion at node I. In these equations, K is the time step, H is the sampling parameter, and beta ij represents the infection rate from node J to node I at time K. Finally, the gamma I represents the healing rate of node I at time K. So we first present the assumptions for the model to be well-defined. The healing rates are larger than 0, and the infection rates are non-negative. We also acquire the following lemma. All the system states lie between 0 and 1, and they add up to 1. This is because each subpopulation can only have these 3 states, and the susceptible level is monotonically decreasing. Now, with the well-defined model, we propose the research questions of this project. Given testing data, how do we construct a stochastic framework that estimates the system states for each subpopulation in the network. What is the estimation error of the stochastic framework that we proposed? And given the system states estimated from testing data, how do we devise a dynamic control algorithm such that the virus is eradicated within exponential time? Here is the estimation framework for our system states. Given the testing data from T1 plus 1 to T2 plus 1, where Cik is the number of confirmed cases at time k, and Dik is the number of recovered cases at time k. We utilize our estimation algorithm to infer the three system states over the network. We first define the testing delay as the length of time between a person's infection and the positive test result is reported. We make the following assumptions, where each infected person has an equal probability pi of receiving a test each day starting from the day after their infection. We model the testing delay tau I as a random variable following the geometric distribution. This is to capture the randomness and the willingness of an individual acquiring a test after infection. Then, the probability of an infected person acquiring a positive test delta days after the infection is calculated as pi times 1 minus pi to the delta minus 1. Recall that the set of testing data is omega ik, where Cik represents the number of confirmed cases, and Dik represents the number of recovered cases at time k. Then we can calculate the number of active cases as below, where the Cik is the cumulative number of confirmed cases, and Dik is the cumulated number of recovered cases. We now define the proportion of daily confirmed cases and recovered cases as where Ni is the size of each subpopulation. We assume that the recovered proportion follows the binomial distribution, where the first term here represents the proportion of active cases, and the second term here is the probability of each active case being recovered. We obtain that the proportion of daily confirmed cases is written as below. The first term here captures the urgency of an infected individual obtaining a test. And the second term here represents the unwillingness or the stubbornness of an infected individual acquiring a test. With the observation model set up, we now discuss our estimation algorithm. From the observation model, we can calculate the change of susceptible level in this equation, and we calculate the change of recovered proportion in this equation. Since the change of three states should cancel out, we then acquire the change in the infection level. Then we assume initial conditions for three epidemic states here, and they do not change beyond the testing period. Therefore, by applying the following equations here iteratively through between T1 and T2, we are able to estimate the three system states. Here on the left, the plot illustrates the daily number of confirmed cases and recovered cases at Lafayette with pi equals to 0.2. And on the right, we compare the estimated susceptible level and the true susceptible level when we start testing at t equals to 20. As we can see here, since we started the testing a bit late, there is a small gap between the two values. This leads on to the question of how do we characterize the error of our estimation algorithm. Here, we get the following result where the estimation error consists of two parts. The first component here depends on the difference between the estimated initial susceptible level and the true initial susceptible level. And the second term depends on the start testing date, T1. Therefore, the accuracy of the estimation algorithm corresponds to the estimated initial condition and how early we start testing. Here is an illustration of the absolute value of estimation error at node Indianapolis. The error changes linearly here with the initial conditions assumed. And the red dots in both of the plots represent when the estimation error is lower than 1%. With the later start testing date, we must assume a lower initial condition for susceptible proportion so that we can acquire accurate estimation results. With the estimation acquired from our framework, we now propose our distributed eradication strategy, where we adjust the healing rate, gamma here. This adjustment can be interpreted as distributing effective medication, medical supplies, and healthcare workers to each subpopulation. We also obtain that with our dynamic eradication strategy, the virus will be eradicated within exponential time. We then compare the average infection and susceptible proportion with control strategy applied at all time and without control strategies. It can be seen that the virus dies out much faster with the control strategy we proposed than with no control. And on the plot on the right, the equilibrium susceptible level is larger than the susceptible level without any control. This indicates that fewer individuals got infected over the duration of the outbreak. We then only enforce the control strategy within a time duration 20 to 50 on the left and 20 to 100 on the right. It can be seen that on the left, if we remove the allocation of resources and healthcare workers from a subpopulation too early during a pandemic, there could be a potential outbreak. While on the right, the curve is relatively flattened with longer duration of control strategy applied. So with these results provided, the decision makers can determine the length of the enforcement of our control strategy needed during an outbreak. Finally, we come to our conclusions. First, we proposed a stochastic framework for estimating the underlying epidemic states from collected testing data. Then we provided an analytic expressions for the error of the estimation algorithm. And last, we proposed a distributed control strategy that is able to eradicate the virus in at least exponential time. And that's all of my project. Thank you so much. Any questions?